Okay, so now we are recording. Right. So I posted a comment there. I think I did. Yes. So let me share my screen with you, and then let us talk through that. So now, can you see the screen? My screen, that is.
Yes, sir.
Yeah. So this is the comment I sent. So I have already asked all of you to submit your choice of paper, which many of you have not done, but that's a different matter. The assignment is really about your understanding. So I don't want you to make a summary of the paper. Summary, I know you can make very well. What I want to see is your impression on what the paper is actually doing and if there are any pros and cons to it. So it is more like a critical assessment than a summary. But I have given you sufficient width, so you can put in whatever is relevant from the paper in summary and along with your comments. So your comments and your critical comments is what I am really interested in.
Okay.
So that's what I want in the assignment. Is that clear?
Okay.
And also, because it's a math finance course, I have rejected some of the choices because they did not have any mathematical methodology or any statistical methodology. That is something that I have to be careful about. Okay. Any other questions regarding the subject matter of the lectures so far?
Sir, regarding the understanding of my own, if there's like some scope of improvement that the paper has mentioned but not done yet, so I can have some like my own thoughts.
You can also make your own.
Like if I have some, I mean,
Yeah, of course.
I haven't gone through my paper yet.
Of course, you
I
have.
mean, I was just looking at it, but there was some.
So the first thing that I want you to do is give a critical assessment of what has been done. And then, of course, if you have some ideas of what could have been done, apart from what the authors have themselves written in the end, you can definitely add that. That would be fine.
I mean, like the critic, what can you exactly? Can you explain the term critical assessment? I mean, how
Okay.
is it different from the actual summary of the paper?
Yeah. Okay. So suppose you are. So let me give you a very simplified example, but I hope you will understand what I am talking about. So suppose you are handling a data which is essentially categorical in nature. You know that the data generating process is really categorical in nature. So it is not at all in a continuum. And then you go ahead and use the standard linear regression to fit that data and make for predictions and all that. How would you comment on that?
They should not use standard linear regression. Like, there are some other categorical models.
And also, what are the pitfalls? So what are the things
Yes.
that are going to go wrong? Some of those things are very obvious, of course, but
Like prediction would not be categorical in some cases. It would be continuous.
So that's what I understand by critical assessment. Another example could be that suppose you are looking at energy trading and you try to take all the assumptions as in the classical Black-Scholes. Would that be right?
No, I guess.
You don't know yet. No. So let me just give you an example that in the say wind energy market. In the wind energy market, there are quite a few engineering requirements you can understand, like because storing energy is very hard. So the only traders who can actually operate in the market are really large players who are going to buy a large amount of energy on a continuous basis. Large amount on a continuous basis. So it's like, suppose CSC is writing a contract for wind energy, hypothetically. CSC can do that, but personally, I cannot do that for my plant. That would be ridiculous. Okay. So that would mean that the error process of the pricing model has to be very carefully selected, because the normal distribution, Brownian motion, these things usually assume non-atomistic behavior. That there are many participants, each participant is infinitesimally small. But if you are talking about the energy market, that is not necessarily true. So some of the assumptions will need to be modified. If a paper directly uses the classical Black-Scholes for energy market, I would be critical about it.
Okay, sir. Thank you.
So that's what I'm talking about. So in context, because all the financial math models have a physical context, which is very important. So in context, whether assumptions are appropriate or not, that is one thing. How a particular data is analyzed, whether that is appropriate or not, that's another possibility. And of course, you can always suggest that, okay, it could have been done better in this way, if you have such an idea. That would be a good critical assessment. All right. So again, any questions on the lecture matters so far? Because we stopped last week. Monday was the special lecture. So are there any questions so far?
So one question around the assignment only. Like in the third assignment, we had to make groups. So do we have to also decide our project also, or will you be suggesting something?
No. The third assignment is a very conventional one. I will give you a problem set which you have to solve and submit.
Okay, and the timeline is around the same, like 20th December.
No,
or
I haven't put a timeline for the third assignment.
Yeah, exactly. Yeah. Okay.
So first, I want to see whether all of you have decided the groups. I looked at the Excel file. Some of you had filled in. I don't know whether it's complete. Is it complete already for the whole class? I didn't check.
I don't think so. Yeah, but many of us have already filled the names.
That I saw.
Yeah.
Also, once your second assignment is fairly on the way, I will assign the third one.
Okay.
So the third one will be a very conventional one. Problem solving kind of.
Okay.
So this is the 5, right? So let me just check how many of you have filled in. Because I thought about 6-7 groups specified. So, is that the right file? Yes. Right. So far I can see 6 groups. You can all see my screen here, right?
Yes, sir.
Yeah. So far I see 6 groups. So there should be a few more. Once that is more or less done, I will assign the problems. Okay. All right. So yes.
Will it be paperwork like exam questions or something kind of project?
No, it will be like paperwork, like exam questions.
Okay.
So all you need to do is write it, take a photo and send me. Or you can actually type, but I guess that may be more time consuming. Okay, so let me begin then with the regular business of the day. So I said that we are going to discuss the solution method of stochastic differential equations. We have already discussed the canonical example, the population growth model, and in general, if you have an Ito process with at least with constant coefficients, how we can solve it using the usual techniques. So what I mean by usual techniques, I mean the techniques you have learned in your high school or in your undergraduate classes with deterministic differential equations. So that is something that you have handled in the past, and the stochastic differential equations are solved using similar techniques with the necessary extensions to take care of the uncertainty. Because finally, our object that we are going to solve for is a probability distribution and not a deterministic function. But otherwise, many of the techniques that you have learned earlier are going to be relevant. And then I asked you to look at Whale-Portstone chapter 6. Chapter 6 is the one that I'm going to talk about today, part of it. So did any of you look at it?
Yes, sir.
So I said that we are going to look at the first order and second order equations because that is reasonable enough. You can of course look at higher order differential equations in real life, but they will occur less often. So it is okay to defer that discussion for the future. We will just look at the two initial candidates which are most common in applications, and again you know how to solve them if the stochastic term was absent. So that's what we will do today. So stochastic differential equation of the first order. So you know that what is a first order non-stochastic differential equation. A usual first order differential equation will look like this. So a0 x prime plus a1 xt equal to 0. So it's a homogeneous first order differential equation. Okay. This is familiar?
Yes, sir.
Yeah. So this you have seen. You have seen in class 12 or wherever. So the change that we are going to make is, of course, we are going to introduce the uncertainty. And of course, the uncertainty will be in terms of a Brownian motion. So our stochastic first order differential equation, the one that we are now going to look at, is of this similar form. So we'll write it in this way just to make it consistent with the non-stochastic version. So I say that a0 x prime plus a1 x dt equal to dv. So this is my canonical form for the first order SD. So I just put a stochastic term in place of this 0 here. This is still in the homogeneous in the homogeneous spirit, but once we are able to solve with this one, we can also easily see how to tackle non-homogeneous equations, because you have done that for deterministic differential equations before. So again, the way to solve this would be to introduce an integrating factor. And if you have an equation of this form, then the integrating factor would be e to the power minus alpha t, where this alpha is actually minus a0 by a1. So this alpha will be minus a0 by a1. That's the integrating factor we used to do in school. So our equation will become, so I multiply both sides by e to the power minus alpha t. I get this form, which I rewrite in this way, because that will explicitly tell me what I am going to get when I integrate. So this left-hand side then would be same as d of e to the power minus alpha txt. So it is like the class 12 problem. On this side, I have 1 by a0 e to the power minus alpha t dv. So on this side, I actually have the stochastic integration to be performed. This side, I already know what to do with. So of course, I solve. I get the left-hand side here, where I assume that my time starts from t0. So I assume that I have a starting time point, which is t0. You can take it to be 0 or any other arbitrary value. But with a t0 starting point, my integral will look like this on the right hand side. The left hand side is of course this. This is the upper limit value and this is the lower limit value. If you want, you can put the t not equal to 0 here and make necessary modifications. But the right hand side is the new one. Earlier we were done with this integration, but now we have to also look at this. But now we know what to do with this, because all these dv integrals we know how to solve. So I write my xt, so I solve, I write this thing in terms of xt on one side, everything else on the other side. So this is my initial value, and this is my integral to be performed. So finally, if I say that x at t naught is x0, so there are two ways of doing it. I can either say that x0 is actually non-stochastic, some known constant, or I can say that x0 is a known random variable. Either way will give me same kind of solution. And then of course I will have some initial conditions with which I will be able to solve the integration constants. So our solution will in general look like this. Xt will be x0 to the power alpha t and then this integral. This is as it's expected, straightforward extension of our high school calculus. Now I know that this is after all a random variable, and also I know that this is normally distributed, because I know that these dv integrals are all Gaussian. So all I need to find are the mean function and the covariance function, which is the autocovariance in this case. So the mean function first, mean function mu xt, that's the notation, and expectation is given by basically expectation of this integral. The other part is straightforward. And of course, the expectation here is 0 because it's a dv integral. That also we know already from earlier discussions. So the mean function is simply given by x naught e to the power alpha t. And again, it is pertinent that if I did not have the stochastic term, then this would have been the solution. Even in the population growth model, we saw the same feature, that if I ignore the stochastic part, then the mean is same as the non-stochastic solution. Here also, the mean function is like this. Going forward, I have to evaluate the autocovariance. So I basically look at the product xt times xs, because I want to find the expectation of that. That would be my autocovariance. So this would be like a product term, and multiplying out and some manipulations, I will get a form like this. So again, I'm skipping these details for two reasons. One is that these are typically routine but boring details which you should be able to work out very easily. And secondly, if you are not patient enough to work it out, well, post on, the book is with you and all these steps are worked out in complete detail. So exactly how this product is evaluated, how this becomes this integral when you take expectation, and everything is worked out step by step in whiteboard. These are fairly routine, fairly easy to understand. So I don't want to talk about it too much. I'll just only say that what you get here is a form of this type from which I finally want to evaluate my autocovariance function, gamma, which is the notation is gamma x st, which will be of this form. Is this clear? So I basically evaluate the expectation of the cross product, xt and xs, and then find the covariance. I know that the expectations are all of this form, so I will subtract that. So what we will do is simply take this first term out. These first terms, they will get cancelled by the expectation product. So what I will be really left with is this e to the power difference type of term. So that would be my form for the autocovariance function. And because I have a stationary distribution here, why is it stationary? Why is it stationary? Can anyone tell me? Because I simply changed gamma x st to gamma xt.
Sir, if the autocovariance function was only dependent on the time gap between S and T,
Yes, that is true. But there is also a t plus s term here, by the way.
yes,
So do we have stationarity for this process?
I cannot see.
I think we had a discussion on the properties of these integrals earlier. Can you recall that? And from that, can you see why? Okay, so that is a question that you should satisfy yourself with, that if I have a stochastic differential equation of this type with a solution of this type, so does it have the stationarity property? Can I simply say that the autocorrelations will be only dependent on the time gap? So okay, so in general, your autocovariance function will be of this form, that is just algebra, no problem there. And if I look at the gamma xt form, as I said, I claim that this stationarity, then it will be easier. The variance is, of course, of this form. So this is tt, so I just write t here. And this is e to the power minus 1 minus e to the power 2 alpha t. So the nature of the variance will be critically dependent on the sign of this term. Now, for obvious reasons, we will continue assuming that alpha is negative, because otherwise we do have a problem here. Okay. So what we are claiming is that A1 and A0 have the same sign. So in the original equation here, A0 and A1 have the same sign. So I know alpha then will be negative. Otherwise, the variance will explode. So all the niceness of the solution will vanish. Do you see that? I need alpha to be negative.
Yes, sir.
So that is an assumption that we will implicitly keep taking from here. So I do have this form of the solution, and it is well defined. The variance is behaving nicely. The mean is easily computable. So I know the full distribution of the solution. So it's a well-defined solution to the stochastic differential equation. Now, if I want to extend it to the whole of the real line, not start from 0, but also extend to minus infinity, then I can also do so. We have already had a little bit of discussion about this improper integral evaluation, under what assumptions it will work and so on. So those assumptions will be required here also. And in fact, given that alpha is negative, we can ensure that those conditions are satisfied. So I can extend it to the negative side of the real line also. And the solution then in general will be of this form. Actually, the form will remain the same as before. And the variance function will be given by this form. Sorry, the covariance function. So again, a little bit of details are being ignored here. I'm not working out, but as I said, the book has all the steps very nicely written out in detail. So just check that. It is not really very exciting, so it is good enough to look at it later on from the book. So what I do have is the following. I started out with this first order differential equation. Initially, we started out with a time t naught, which could be 0. So basically, first I'm looking at half of the positive half of the real line, let's say. I know what the solution look like. This I can easily find out from the integrating factor. And then I evaluate the mean and the autocovariance function. Okay. If I want to extend it to the whole of the real line to the negative half also, I have to put in this improper integral here, and I can still make do because of the form of the integrand inside, and the form of the equation will remain the same, and the covariance function will become of this form. So that's the first order differential equation. Of course, the solution is a Gaussian process. So given that I have already evaluated the first two moments, I have evaluated the solution completely. So just to summarize, if I have this xt process, this is minus infinity, by the way. So from minus infinity to plus infinity is a solution to that stochastic differential equation. Then it will be of this form. X naught will be of this form. And I already have written out the mean and covariance functions. A little bit of discussion about how to extend this to the improper sense. In the improper integral, I know what are the conditions required, so I can extend it to the whole of the real line. And a more general solution where, as I said, if I have an initial condition on x naught, and suppose x naught is a known random variable, so a random variable with a known distribution, then the solution, the general solution will look like x equal to c to the alpha t plus x naught. So this is just like the specific solution plus the general solution gives me the complete solution. Where c is a known random variable. I know what the distribution of c is. Sometimes we specialize even further and we say that c is actually a known constant. That's even better. So this is actually also the unique stationary solution of this first order stochastic differential equation. Any questions? Any questions so far? Because most of the things are direct extension of our deterministic solution technique. The additional part is, of course, taking care of the uncertainty and then evaluating the probability distribution of the solution. But this is so far using only straightforward results and some manipulations, which I'm not going to discuss, but you can look it up. Okay, so this is clear. We can move forward.
Yes.
Okay, so let me then move forward to the second order solution. Again, we know how to solve second order differential equations. We learned that in high school. The canonical form now will be like a0x double prime, a1x prime, and a0x equal, this whole thing is dt. There should be a bracket here. So again, there is a mistake here. The whole thing is within a bracket equal to dv. And of course, as in the deterministic case, we will use the characteristic polynomial, or we will solve the quadratic equation. So if I just work with a simple example, so suppose my equation look like x double prime twice x prime plus px. So I have a0 equal to 1, a1 equal to 2, and a2 equal to 2. It's a second order differential equation, so I will need two initial conditions. So suppose I say that x0 is 0 and x0 prime is 1. So these two initial conditions will eventually help me to determine the constants of integration. So my characteristic equation will be of this type, and the solution will look like -1 plus minus I. So the delta is negative here, so the solution will have imaginary parts. And we know how to handle this. We use the trigonometric transformation. So the roots will be looking like phi1 equal to e to the minus t cos t and phi2 e to the minus t sin. So again, this is something that you can do in your sleep. So I'm not going to discuss the details. So I have this particular equation, stochastic differential equation, and the solution roots will be this thing. So the general solution, we know how to write it out. It will be xt equal to c1 phi 1, c2 phi 2, and then integral of one of these dv's. So it is like the same technique that we use for the non-homogeneous case. Here, only the right-hand side addition is in terms of the different, in terms of the dv term, the stochastic disturbance. So this is the general form of xt. So this would be the general form of x prime t. So if I differentiate this, and then I solve, because I am given a couple of initial conditions here. So I solve, and I can find out c1 equal to 1 and c2 equal to 2. So basically my solution will be, this c1 will be 1. So this phi 1 plus twice phi 2, and then this integral. That will be the general solution. And of course, this is a random variable. So I need to understand the mean and variance. So the expectation. So here it is very unclear. So the expectation is actually going to be e to the power minus t sin t. If you evaluate the expectation here, you will see that the expectation is e to the power minus t sin t. The variance will be sigma square integral 0 to t. So this is not right. I should write it down. So this is e to the power minus 2s sine square s ds integral 0 to t. Okay, so I'm sorry about this thing. This is very, very unclear. I did not check before. But can you write it down? Or should I use the board? I can use the board if you want.
No, sir, I think this is okay because it follows directly from that properties of stochastic integral.
Exactly. Follows directly, but I'm still sorry about the unclearness of this page. The scanning was not done well. So this is just sigma square outside 0 to t to the power minus 2s sine square s ds. So it will be very easily done if you look at, as Subhrajit pointed out, that just look at the term here and evaluate the second moment. Okay. Any other thing that requires discussion? So we have just talked about the second order differential equation here. The non-stochastic version you know how to do, and we use the same technique. We use the characteristic polynomial. So we are solving a quadratic equation. The general solution form is given by this equation here, and then we use the initial conditions to evaluate these arbitrary constants, which can be easily done. And finally, to complete the solution, we need to show the first two moments, which are also reasonably easy in this case because of the form of the solution here. And we can find out these two in a relatively straightforward manner. Okay. Any questions here?
Yes, sir.
All right. So we have actually discussed some of the solution techniques. So I'll just scroll back because this is where we started solving stochastic differential equations. So we started out with the population model, Ito process. Then we talked about specifically the first order, second order equations, because in real applications, those will be commonly occurring. But one question we kept back initially, that how do we know that solutions exist? Or rather, what are the conditions given which solutions will exist, and also under what conditions the solution will be unique. See, so if you have done this formal differential equation course earlier, you know the initial value problem, and you know how to guarantee existence and uniqueness of solution. Do you remember those things? Have all of you done it? So this would be the conventional ordinary differential equation theory. But are all of you familiar with that? Just a quick check. Has all of you done this thing before in the deterministic case?
No, sir.
Ready? Yes or no?
No.
No. Oh. You don't have differential equations in your undergraduate anymore?
Sir, in which part we should
Huh?
have? Yeah?
Huh? Sorry?
I mean, which chapter does it concern? Growth model.
I mean, if you are doing a course on ordinary differential equation, then it will come in the beginning, the initial value problem.
Okay. I don't remember.
We had initial value problem, but we didn't have this one.
You didn't have what?
This thing.
Which thing? The existence uniqueness part.
Yeah.
No, we had existence uniqueness part.
We had unique existence parts.
You must have.
Long proof was there.
Otherwise, how do I know what I'm talking about makes sense?
That is why we could like guess those form of the functions and then check whether those.
Yes, yes.
So,
Exactly.
yes, we had those
You
existence.
must have had it. You must have had it. So you had something like Lipschitz type conditions. Are those?
Yes. We had it. Yes.
So Vaishnavi, maybe you need to look back on your notes from earlier, because any differential equation course will start
Yes, sir.
with that, I'm sure. At least that's how it did in our time. So that should not change.
Actually, we had like a collection of a bunch of mini models. So we don't actually recall like whether we had
No.
this or that.
It's not about specific models. It is about the general principle of guaranteeing the existence and then guaranteeing the uniqueness.
No, that was included.
That must have been there, because you see, once you come down to specific models, then those conditions also translate to specific version of those conditions. Those you cannot really recall for everything, but as a general principle, there are some basic theorems that we were taught. So that's what I am referring to. All right. So when I do that, actually, it will be a refresher on the non-stochastic example also, because the examples I'm going to give are actually non-stochastic examples. So because the conditions here are so fundamental that if they are not satisfied, then even non-stochastic versions will either not have solutions or won't have unique solutions. So it is as simple as that. So basically, now we will talk about that question, that how do we guarantee existence and uniqueness? We have already done some solutions, but it is still was like fishing in dark waters. So now we talk about the existence and uniqueness solutions, and this is the back page. So I will again try to read it out to you, and you should write it down. So this is the main theorem here. So the theorem is that, let's suppose capital T is some positive real number. B is a function from 0 to T cross R to the real line. So this is 0 to T cross R to R. C sigma, the volatility, is another function, again from 0 to T cross R to R. So I have two functions, B and sigma. They are measurable functions. So now I have to be a little bit formal. I need these functions to be measurable. Otherwise, the proof of the theorem will have a gap. What are the conditions? So the first condition that I put here is that absolute value of B plus absolute value of sigma is bounded by some constant C times 1 plus mod X. So there is a bound on the sum of these two functions. The bound is independent of time. That is critical. Bound is independent of T, the first argument. And it is a linear in absolute value of the X argument. X is again real valued. And this condition I call the star condition or E condition. This is the E condition because this is going to guarantee the existence of a solution. So the first condition is the sum of absolute values of these two functions must be bounded by a term C into 1 plus mod X. The second condition is about the differences, the changes. So again, I bound the sum of the absolute changes. So this is btx minus bty absolute value and sigma tx minus sigma ty absolute value. So the absolute differences sum is bounded above by some constant d times absolute value of x minus y. So x to y is the distance I am traversing on the x line, on the value line. So the total change, the absolute total change in the two functions is bounded by the distance I am moving. So this is, as I said, this is like our Lipschitz condition. So those of you who remember this is the Lipschitz condition that we had in the non-stochastic version. Of course, then we did not have sigma, of course, but same spirit. So this condition I call star or the U condition because this guarantees uniqueness. So the first one keeps things bounded and the second one keeps the changes bounded, where C and D are two constants. All right, so are the conditions clear? I have not yet written the objective, but first the conditions. So what I am interested in is the stochastic differential equation dxt equal to b dt plus sigma dv. That's why I had two functions, b and sigma, that you can easily understand. So the SD is dxt equal to b dt plus sigma dv in 0 to capital T on the timeline with expectation of x naught square finite. This is a very reasonable condition that we have to keep. That we know why from the integration theory that we have done earlier. So what is the theorem saying? The theorem is saying that if this B and sigma functions satisfy these two conditions above, the E and U condition, then this particular stochastic differential equation has a unique, so it has a solution, that so the solution exists, it's unique, and it is also T-continuous. So that's our Kohlberger continuity beauty, that beautiful theorem. So I do have a unique T-continuous solution, xt, which will be FT adapted because I started out with measurable functions. So xt will be FT adapted, and the square integrability condition for the earlier capital V class of functions, that is also satisfied. So expectation of the integral xt squared dt will be finite. So I have these two conditions, the E and the U condition. If they are satisfied, then my stochastic differential equation as written here will have a unique T-continuous solution, which is FT adapted and square integral, which would guarantee finite variance. So is the statement of the theorem clear?
Yes, sir.
Yes, sir.
So if you, after this class, if you go back to your ordinary differential equation textbook and look at the theorem there, you will see essentially similar conditions. Of course, these are extended to take care of the stochastic part, but in spirit, that theorem and this theorem are the same thing. Rather, this theorem is an extension of the theorem that you can find in the ordinary differential equation text. Of course, the extensions are non-trivial because we have all these uncertainty to take care of, but we know what to do. We have already developed the machinery necessary for that. Okay, so now for the examples which illustrate why these conditions are necessary. And as I said, these examples are all for deterministic situation. So if these conditions are not met, even the deterministic equations will fail. So this is like also a refresher on your ordinary differential equation course. So the first example is, take this equation dxt dt equal to xt square. This is a ordinary differential equation, no stochastic part, x not equal to 1. And I can easily see, and you can also easily see that it has the unique solution xt equal to 1 by 1 minus t, but only for t between 0 and strictly less than 1. So I cannot define a unique solution of this equation over an unrestricted domain if I want. I cannot choose any capital T. So it will only work up to the left of 1, from 0 to 1, not included. The reason is obvious because the form of the solution explodes. You can see the solution. But how does it relate to our existence and uniqueness conditions? If I look at the B function, because there is no sigma function here, sigma is 0. The B function is xt square. Okay. So if I look at this condition, this will not be satisfied by the B function because the B function has a higher order than mod x. So the E condition fails, which means I should not have an unrestricted solution existing, which is indeed true. I can see directly that a solution over an unrestricted domain does not exist. So that's a straightforward illustration in actually in deterministic situation where the E condition is critical. The E condition is indeed important. So it is impossible to find a solution for unrestricted domain. Okay. Is this okay?
Yes, sir.
Right. The other condition was about the uniqueness part on the Lipschitz type condition U. For that, the choice of function is dxt dt equal to 3x power 2/3. Now you understand the trick. The power is less than 1, so as soon as I differentiate, I will have xt in the denominator. So again, x naught is 0, and you can easily show that this has more than one solution. This is infinitely many solutions. What is the form of the solution? The form of the solution will be xt is 0 for t less than or equal to a, and t minus a whole cube for t greater than a. And a, choice of a is arbitrary. I can take any positive A and it will be a solution for this differential equation. So there is no unique solution for this. So infinitely many solutions. For every choice of A, I have a corresponding solution. How does it tie in with my uniqueness condition? Again, the B function here is 3x power 2/3. And now go back to this Lipschitz. I can show that this difference, because sigma is not there, sigma is 0, this difference cannot be bounded by D modulus x minus 1. Because in the difference part, I will have x in the denominator. So I can make it explode. I can make that explode. So uniqueness will fail for this particular B function. And that is directly demonstrable because I have this class of solutions, infinitely many of them, for this particular differential equation. So again, in summary, for our stochastic differential equation of this form, this is our usual form, B dt sigma dV. To guarantee existence and uniqueness of solutions, I need these two conditions to be satisfied. One on the magnitude of the functions and the other on the change of the functions. If any of them fails, even the deterministic counterparts will fail, in the sense that they may not have solutions at all, or they may have multiple solutions, non-unique solutions. So you can understand that if I move on to stochastic part, it will be also true. These conditions will be indeed necessary. So, okay. So, are there any questions? Because I will stop here. All right. So then we are done with today's class. But you should look at Whale-Portstone for the differential equation solutions, and also do a little bit of revision on the ordinary differential equation theory that you have done earlier, because this theorem and the subsequent discussions that I just did are essentially straightforward extensions, not straightforward, but extensions of those theorems that you studied in your ODE class. Okay, so I'll stop here and we will meet again on Monday.